Okay, so we've been adding and subtracting matrices, and then we did some multiplication of matrices. So you're probably thinking, well, next we're going to do some division. No, we're not. Why? Because we don't actually do the act of division with matrices. What we do though is something called the inverse. Okay, the inverse, which is effectively undoing a multiplication. Okay, what it does is undoes a multiplication. So when you look at it in sort of arithmetic, if we think of matrix A times by matrix B equals C, and we want to figure out what's in B, we want to solve for B. So ordinarily, okay, if this was algebra, you go A times B equals C, then we divide both sides by A. Well, we can't do that with matrices because we can't do that division. Okay, so what we do is we undo the effect of timesing, which is what dividing does. We undo the effect of timesing by this thing called an inverse. An inverse. So the inverse of A undoes the effect of A. So inverse of A times by A gives you the identity matrix. Now, if you times anything by the identity matrix, it's like timesing it by 1. So effectively, this, they all cancel out, so you just get left with that A. Okay, so that's what that does. Now, a little thing to note here that you're getting to more in general maths is see how A is on that left-hand side of B. That means that the inverse has to be on the left-hand side. As you know, when you're multiplying matrices, the order in which you do it is important. So we have the inverse of A over here and the inverse of A over here. You'll notice it's on that left-hand side of C because it's on the left-hand side over here. Okay, so that's a big lead up to tell us about the inverse. All right, so only square matrices have an inverse. Okay, only square matrices can have an inverse, but not all square matrices have an inverse. All right. Now, we're going to focus on the 2 by 2 matrix. Why? Because that's how we can do it by hand. When we get to general maths and you have a CAS, then you can do all the others on your CAS. However, your 2 by 2 matrix, to find an inverse, we can do that by hand relatively simply, relatively straightforwardly. Now, as I was saying, that only square matrices have an inverse. However, not all square matrices have that inverse. So first off, we need to do something called the determinant. We need to find the determinant. So we need to determine whether that matrix has an inverse. Okay, so with the 2 by 2 matrix, if we've got matrix A, then we have our 4 elements. So I've called that element A, B, C, D in those positions. So row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. Okay, so that determinant of A is equal to A times D take away B times C. So that's A times D, that diagonal, take away B times C, that diagonal. All right, so what we're really looking for here is to see whether or not if that determinant is equal to 0. So if it's equal to 0, this means it has no inverse, okay? So we're looking to see if that determinant is 0. If it is equal to 0, then we have no inverse, we can't go any further. If it's anything other than 0, anything other than 0, then we can find the inverse. Okay, for anything other than 0. All right, it doesn't matter if it's positive or negative. That has no effect on it, all right? It doesn't matter if the inverse, if that determinant is positive or negative. It only matters if it's 0 or not. Okay, so once we've determined whether or not a matrix has an inverse, a square matrix has an inverse, then we need to find it. Okay, I know this looks complex, but it's fairly straightforward. So this is to find an inverse of a 2 by 2 matrix. So again, we've got our matrix A. We've got the element there, there, and there, A, B, C, and D. So to find that inverse, okay, so the inverse of matrix A is equal to 1 over AD minus BC, which was the determinant. Okay, 1 over that determinant times by this matrix. Now this matrix is the original matrix rearranged a little bit. So what we do is we flip the position of the original A and D. So that diagonal gets flipped. So you can see we've now got D up there and A down there. Now on this diagonal, we times those numbers by -1. Okay? All right, so if you think about it, we flip that diagonal. Oh my. And then we times the elements on that diagonal by -1. Okay? And then we get left with our inverse. So with a fraction times by a matrix. Now you can then times that fraction into the matrix, like we were doing earlier with that scalar multiplication, but you can leave it there as well. Either way, it's correct. Let's go through some of the worked examples I've got here. So I've got matrix A equals to 4, 5, 1, 2. Find the inverse of A. First off, we look to see what the determinant is. We've got to check that determinant to see if A's got an inverse before we start doing all of that. So that determinant A is equal to AD minus BC. So we've got 4 times 2, 4 times 2, take away 5 times 1. All right, so our determinant is equal to 8, take away 5 equals to 3. All right, as determinant is not equal to 0, that means, therefore, A does have an inverse. Okay, so now we're going to go ahead and get to work on finding that inverse. So our inverse is equal to 1 over AD minus BC, which was the determinant that we just figured out. So it's 1 over 3. So let's look at this matrix bit. We flip that diagonal. So it was 4, 2. Now it's 2, 4. You can see there it's 2, 4. And that diagonal, we times those numbers by -1. So 5 times -1 is -5. And 1 times -1 is -1. Okay, I can leave it like that, or I can multiply the fraction into the matrix. So 2 over 3, negative 1 on 3, negative 5 on 3, or 4 on 3. Okay, so both of those, are correct. Okay, so now we have matrix B, 2, 6, negative 3, 4. Find the inverse of B. So first off, we figure out, well, what's the determinant? Okay, so our determinant is 2 times 4, take away 6 times negative 3, so I get 8. Now negative 6 times by negative 3 gives me positive 18, so that determinant, is not equal to 0, therefore we can find an inverse. Okay, so what's our inverse? Our inverse is 1 over that determinant, so 1 on 26, and then I look back at my original matrix and I look at the leading diagonal and I flip that. Then I look at the other diagonal and I times those numbers by negative 1. Now, I'm going to leave that fraction looking like that because 1 over 26 is a bit of a yucky fraction, so I'm just going to leave it like that. Okay, so matrix C is 3, 9, 2, 6. Find the inverse if it's possible. Okay, so first off we figure out that determinant. Our determinant is that diagonal, 3 times 6, take away that diagonal, which is 2 times 9, so we've got 18 minus 18 equal to 0. So that means our determinant of C is equal to 0, therefore we can't find an inverse. So what we then say is that we say that matrix C is singular and does not have an inverse. Okay, but basically what I need you to know is that at this point is that if that determinant is 0, we can't find an inverse. If it's anything other than 0, we can find an inverse. So let's look at the following matrices and we find the inverse if it exists. So first off, matrix A, the first thing we're going to do is find that determinant of A. Okay, so I look at my diagonals. So that's 2 times 4, so that's 8, take away 2 times 5, so that's 10. So my determinant of A is equal to negative 2. Okay, so yes, there is an inverse. Okay, so what is that inverse? So the inverse of A is equal to 1 over negative 2, but I'll put the negative out there. Okay, now I look at that diagonal and I flip the positions, so that becomes 4 and 2 down there, and 2 and 5, I times both of them by negative 1, so 2 times negative 1 is negative 2, 5 times negative 1 is negative 5. Now this one I might put the fraction in to make it all one matrix. So inverse of A equal to, so negative a half times by this matrix. If you remember, that means you've got to times each of the elements by negative a half. Okay, so 4 times by negative a half, so 4 times by a half is 2, so that's negative 2. Half times by, negative 1/2 times by negative 2 makes positive 1. Negative 5 times by negative half is positive, and that's 5 on 2. And positive 2 times by negative a half is -1. Now I decided to times this by that fraction to make it all one matrix because I knew we'd end up with mostly whole numbers. Just a sec, sorry, that was a door slamming. Okay, so now we look at matrix B. So first off, what's the determinant of B to figure out whether or not we have an inverse? So look at the diagonal. 5 times 4 is 20. Take away 7 times 3, which is 21. So that's -1. So yes, there is an inverse. Okay. So inverse of B. The inverse of B is equal to 1 over -1. We'll fix it up in a sec. And then I flip that diagonal. So 4, 5. Then I times the elements on that diagonal by -1. So that becomes -3, -7. Okay, so 1 over -1 is 1 divided by -1, so that's -1. So I'm going to put this into here, like times this fraction by the matrix. So in other words, timesing all the elements by -1. So that becomes -4, +7, +3, and -5. Okay, so C. First off, what's the determinant of C? I might actually write this underneath. Determinant of C is equal to 4 times 3, which is 12, take away 6 times 2, which is 12, equals to 0. Okay, so determinant is equal to 0, therefore no inverse. So I can't go any further. Okay, so let's look at D. That determinant of D is equal to 3 times 1, which is 3. Take away 4 times -1, which is -4. So that's 3 plus 4. So that's 1. Okay, so it's not equal to 0, therefore we can find an inverse. The inverse of D is equal to 1 on 1. Flip that diagonal, so 1, 3, times the elements on that diagonal by -1. So -1 times by -1 gives you +1. 4 times by -1 is -4. And of course, timesing everything by 1 divided by 1, which is 1. We just end up with 1, -4, 1, 3. Now, how we end up using the inverse is when we are solving matrix equations. So here I have that matrix times by that matrix equals to this one. So you can see this matrix here that I've called matrix X is X and Y, okay? So this matrix times by X and Y gives us this. Now we want to solve this so we can figure out what this X and Y are, what these unknowns are. So this is matrix A times by matrix X gives me matrix C. So we know in normal algebra that we want to get X on its own to solve for it. So that's what we're doing here. We want to reverse the effect of timesing by X by timesing by the inverse of X. So looking at this, that determinant of A, we've got 4 times 2, which is 8, take away 3 times 1, which is 3, so That's 5. Therefore, that inverse exists. Okay, so the inverse of A is equal to 1 on 5, 2, 4, negative 3, negative 1. Okay, now this is where I find it a good idea to physically do the arithmetic, the algebra. Now I'll write it out as well as talking about it. So I've started with A times by X equals to C. So that's matrix A times by matrix X equals to matrix C. And we want to figure out for X. Okay, so I want to undo the effect of timesing by A that we did here. Now remember, we can't divide, but what we can do is times A by X inverse. You can see here, I've got inverse of A. I've got the inverse of A times by A. Now they'll end up cancelling each other out, so we just get left with X on this side. So then, of course, as you remember, what we do on one side of the equal sign, we have to do on the other. So I have inverse of A times by matrix C. So these two cancel out. So I get left with matrix X is equal to the inverse of A times by C, times by that matrix C, which is what we have here. And here I've done the workings out for us. So this was the inverse of A. Now, when I did this, I decided I'll do that, leave that fraction till last. So I did my matrix multiplication. So times the rows by the columns. So 2 times 10 plus negative 3 times 5 to give me the first element, first row, first column element. Negative 1 times by 10 plus 4 times by 5 to give me the second row, first column element. So you can see I get 5, 10 there, and then I've times it by the fifth to come out with 1 and 2. Now that 1 there, because it's where the X is, remember X is equal to XY, and now we figured out that's equal to 1 on 2. Now remember, when you have two matrices that are equal to each other, that means that those elements are exactly equal to each other. So that means X must be equal to 1 and Y must be equal to 2. Okay, so let's do this one here. So first off, I might say A times by X is equal to C. All right, so what's my determinant of A? Okay, so that's the diagonal. 3 times 1, take away 2 times 5, which is 10. So the determinant of A is equal to negative 7. All right, that means there is an inverse. We can proceed. All right, so that means that inverse of A must be times on that side and on that side of the equal sign. And because the inverse of A was on the left-hand side here, that inverse of A has got to be on the left-hand side here. These two cancel out, so you get left with X equals the inverse of A times by C. Okay, what's my inverse of A? Inverse of A is equal to 1 on negative 7. Okay, flip those, so I get 1, 3 times that diagonal by negative 1, so negative 5, negative 2. Okay. Alrighty, so that means I've got x equals to 1 on, or negative 1 on 7, 1, negative 2, negative 5, 3, times by 12, 13. Now, of course, you can use your calculator to help you out here. If you had a CAS calculator, you could do this on there straight away. Okay, so I've got 1 times 12 plus negative 2 times by 13. So that's negative 26. Then negative 5 times by 12 is negative 60 plus 3 times 13. So that would be 39. Okay. So x equals negative 1/7 on, I'll get my calculator to help me out. So 12 minus 26, negative 14, and negative 60 plus 39 gives me negative 21. Okay. All right. And then you can see, oh, look at that. They're both divisible by 7. So x equals, so negative 1/7 times by negative 14 will give me a positive answer. So that's 14 divided by 7 is 2. And negative 21 divided by negative 7 give me positive 3. So x equals to 2 and y equals to 3. One last one. I've got a times by x equals to c. All right, so let's see whether or not we can do it first. So our determinant of a is equal to 1 times negative 3, which is negative 3. Take away negative 5, take away times by 2. So that's negative 10. So determinant of a is equal to negative 3 plus 10. So that is positive 7. Okay. So we can do that. So our inverse of a is equal to 1 on 7, negative 3, 1, flipping that diagonal, then timesing that diagonal by negative 1. So 2 times negative 1 is negative 2. 5 times negative 1 is positive 5. Okay. So we've got a times x equals c. So I've got to times both sides by the inverse of a. Okay, get left with that. Okay, so that means x is equal to 1 on 7, negative 3, 5, negative 2, 1, times by c, which is 9, 12. Okay, equals 1 on 7. So negative 3 times by 9 is negative 27 plus 5 times 12, which is 60. Then down here I've got negative 2 times by 9, which is negative 18, plus 1 times 12, which is 12. Okay, so x equals 1 on 7. Okay, again, I'm going to use my calculator to help me. Negative 27 plus 60 equals 33. And negative 18 plus 12 equals negative 6. Okay, now as I'm wanting to figure out what x and y is, I can't leave it like that. I've got to multiply that fraction into there. So x equals 33 on 7. Need that a bit bigger. 3. And that's negative 6 on 7. So therefore x equals 33 on 7. Y equals negative 6 on 7.